Hey, what's up, my chemistry people? Who is ready for a free response practice question? It's currently trending. Answer the following questions related to the properties of magnesium and aluminum. Boom! Take a moment, pause the video, look at the Lewis electron dot diagram and the electron shell diagram for those two elements. Part A. Write the complete orbital electron configuration for a neutral atom of magnesium in the ground state. Always like to use my periodic table when I'm doing electron configurations. Magnesium is right here. We've got 1s, 2, boom. 2s, 2, boom. 2p, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 3s, 2, boom. Orbital configuration complete. Part B. Write the complete orbital electron configuration for a neutral atom of aluminum in the ground state. Notice that aluminum has one more electron than magnesium, and it's going to go into that first 3p orbital. 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 1. Aluminum. Now, why in the heck are we doing electron configurations? I thought that was last unit. Well, remember, electron configurations and number of main energy levels is a really important part of understanding periodic trends. So let's take a look at part C. It says the table below represents the first ionization energy for the elements in period 3. The missing first ionization energy values are 496 kilojoules per mole, 578 kilojoules per mole, 738 kilojoules per mole, and 789 kilojoules per mole. Use these values and your understanding of the trend of first ionization energy to complete the table below. All right, as we focus in on period 3, we might just be saying to ourselves, oh, obviously the first ionization energy is going to increase as we move from left to right across the period because the number of main energy levels stays the same and the effective core charge is increasing, which would make it more difficult to remove an electron and therefore increase the first ionization energy. However, we have to remember two important exceptions that occur to that trend. The first one is here in between the S and P block, and the second one is here in between group 5A and 6A. But otherwise, the general increase in first ionization energy occurs. All right, so sodium is definitely going to have our lowest first ionization energy. Effective core charge of +1. It's not going to take a whole lot of energy to yank that electron away. Boom, done. However, as I think about the remaining first ionization energies, I need to keep in mind that although the energies will increase in general across the period, there is an exception between magnesium and aluminum. So I'm going to put 738 kilojoules for magnesium, so definitely an increase between sodium and magnesium, but then we're going to decrease again. So we're going to go back to 578 for aluminum. And then we'll continue to increase 789 kilojoules per mole for silicon. Now, as you think about why, come back to the orbital notations that we just drew out in parts A and B. Notice that magnesium has 2 valence electrons in the third main energy level, and they're in the S sublevel, while aluminum has 3 valence electrons in the third main energy level. One of its electrons is in the 3p sublevel, and those p orbitals do not penetrate the nucleus as well, and therefore it's going to require slightly less energy to pull off this first electron for aluminum. Part D. Explain why the first ionization energy of sulfur is lower than that of phosphorus. All right, so now we're looking at these two elements here. Again, we would think that the ionization energy would increase from phosphorus to sulfur, because sulfur has a larger effective core charge. However, the first ionization of sulfur is actually slightly less than the first ionization of phosphorus. Now, again, I'm going to draw out the orbital notations for these two elements, even though it's not required. I think it's a great way to help visualize what's going on and how we can explain this exception to the trend. All right, here's the orbital configuration for phosphorus. Here's the orbital configuration for sulfur. Sulfur has one more electron than phosphorus. And notice where that electron fills. In phosphorus, we put one electron in each of the 3p orbitals. But when we get to sulfur, that extra electron pairs up with one of the electrons in that first 3p orbital. That pairing causes some additional repulsion and therefore makes it slightly easier to pull that electron away, requiring less ionization energy. The 3p electrons in phosphorus are all unpaired. In sulfur, 2 of the 3p electrons are paired. This pairing in sulfur increases the repulsion between electrons and reduces their attraction to the nucleus. So, less energy is required to remove the first electron in sulfur. Boom! 2 points. Part E. Which element from period 3 does the table of successive ionization energies below represent? Explain. So now we're looking at not just the first ionization energy, but subsequent ionization energies. The energy required to remove each additional electron from a neutral atom. We know the element is from period 3. We have to decide which one. As I scan the list of ionization energies, we're looking for the largest jump in ionization energy. Notice that occurs here between the third and fourth ionization energies. The element is aluminum. The table shows low first, second, and third ionization energies relative to the fourth, indicating the presence of 3 valence electrons, which is true for aluminum. The dramatic increase in the fourth ionization energy indicates removal from a lower energy level. Boom! If you're confused on this, let me bust out my art skills. Aluminum, 13 positive protons in its nucleus. 1, 2, 3 main energy levels. 2 electrons in the first. 3, 4, 5, 6, 7, 8 in the second. 1, 2, 3 in the third. Not so much energy to pull that first one. A little more to pull the second, because now there's less repulsion. A little more to pull the third, because again, a little less repulsion. However, notice now that we've lost an entire energy level. So by the time we get to the fourth ionization energy, by the time we want to remove our fourth electron, it's held much more tightly to its core. Part F. Write the complete orbital electron configuration for the most commonly formed ion of the element chosen in Part E. Alright, we've decided it's aluminum, but it's aluminum that has lost 3 electrons. We've already written out the orbital notation for aluminum, for a neutral atom of aluminum, in Part B. I'm just going to copy that down as a starting point for Part F. But realize it's the aluminum ion. It typically loses its 3 valence electrons. Goodbye, adios, sayonara. So we're left with a configuration for the aluminum ion that looks like what you have on your screen. We've completely lost the third main energy level. Subpart I. Identify one other neutral atom or ion that is isoelectronic with the most commonly formed ion of this element. Alright, well, as you take a look at the configuration here, we've got a completely filled first and second main energy level. We've accomplished a noble gas configuration. The noble gas that's going to form when aluminum loses its 3 valence electrons, neon. Boom! And we are done.